temperature superconductor in the second half. So I'm Peter Wahl from the University of St. Andrews, and the first talk in this morning will be about heavy fermion superconductors by Filip from Los Alamos National Labs.
Thank you, Peter. Am I on now? Okay. Good morning, everyone. Thank you for joining us this morning. And I'd like to begin by thanking Herman, Isabel, and Lenny for putting together this school. It's really been very enjoyable for me, and it's a great pleasure and honor to have the opportunity to present a lecture on heavy fermion superconductivity. I'm from Los Alamos National Lab.
¿Has ido a decir Los Alamos? ¿Dice Los Alamos? No, that's well.
All right. I think in general I can. I'm pretty sure I don't have an extra microphone on me. Okay, so this is the town of Los Alamos National Lab. It's buried in the sort of tail end of the Rocky Mountains in the southwest of the United States. It's beautiful. It has sunshine 300 days of the year. We get snow in the wintertime because we're at such nice elevation. So there are really wonderful things about it. But it's remote for a reason, because this was the origin of where the Manhattan Project was developed. And so, quite honestly, it's a real pain in the neck to actually get to Los Alamos in general. And that was done on purpose so that they could, develop the nuclear bomb in secret. And so you might be wondering why, in fact, actually, is there somebody from Los Alamos National Lab coming here to talk to you about heavy fermion superconductors. And in fact, it has its origins from the weapons program. And when they were enriching plutonium, in fact, the helium-3 isotope was a byproduct. And so Los Alamos National Lab was one of the places where you could actually get the helium-3 isotope. And so this was the origins of low-temperature physics at Los Alamos. And they were interested at the time, just after the war, in studying the properties of fluids for hydrodynamic codes. And so helium-3 being an idealized fluid, they were interested in studying this. Now, if you're worried about sort of the nuclear weapon, you're also worried about the electronic structure, the chemistry and bonding, and so there was an interest in understanding the properties of f-electron materials, so low temperatures and f-electron materials. You were really in the right spot to make progress on heavy fermions, and that's historically why Los Alamos has played a role in heavy fermion conductivity. Okay, so I thought we've heard several people mention heavy fermions sort of in their talk as examples of high temperature superconductors. I thought I would try and make this lecture pedagogical and really start about sort of the notions of heavy fermions and what we basically know before I get to superconductivity, and then I'll sort of rapidly go through sort of a brief history of heavy fermion superconductivity and kind of naturally evolve into the open questions, which are actually, in fact, the same questions that we're dealing with in cuprates and nictides, organic, other classes of unconventional superconductors. Okay, so we're dealing with, in this school, about electronic mechanisms for high temperature superconductivity. And if you go back of course, the prevailing view was that magnetism was bad for superconductivity. And so you see here examples of lanthanum aluminum 2 that is doped with gadolinium, a magnetic impurity. And you see here that Tc drops very precipitously when you add magnetic impurities. In fact, you only need about 0.5% of gadolinium in order to suppress superconductivity completely. And so this was known to be true for a variety of conventional superconductors, and it didn't matter sort of what kind of magnetic impurity you put in. And in fact, actually, if you put in cerium, which at the time was known to be a Kondo ion, which I'll explain in a minute, you can see actually, in fact, that Tc falls with doping is in fact even more rapid than the Abrikosov-Gorkov theory that is known to explain how superconductivity is suppressed in the presence of magnetic impurities. And they understood this, in fact, actually is that the pair-breaking parameter that goes into the Abrikosov-Gorkov theory becomes temperature dependent and actually reaches a maximum when you reach the Kondo temperature, in fact. And so you get this re-entrant behavior of the superconductivity where the system first becomes superconducting, then goes normal again at lower temperatures as you're reaching the Kondo scale. So magnetism was bad for superconductivity. The Kondo effect was even worse. Okay, so what is the Kondo effect? So if you take a normal metal and you add a non-magnetic impurity, so you have some sort of impurity potential, we know that this just generally gives rise to some scattering, and in fact this is responsible for your residual resistivity at low temperatures. It just provides some elastic scattering. However, if you put a magnetic impurity in the system, and now you couple this local moment, S, via some magnetic exchange to the spin of the conduction electrons, it was found that in fact this is a resonant scattering process. And so when you look at the resistivity as a function of temperature here, this is lanthanum hexaboride doped with small amounts of cerium, you in fact get a resonant scattering process, so the resistivity increases as you decrease temperature until it sort of rolls over at low temperatures. And this is, at the single ion level, the Kondo effect is a very well understood many-body problem. And it was Ken Wilson and the renormalization group theory that actually identified the fact that at low temperatures, really what you have is a Kondo singlet, so you screen the magnetic impurity by enough scattering of this conduction electron with the local moment. So in effect, you basically sort of screen out. You get a non-magnetic singlet, so you lose your magnetic impurity, and it's a local Fermi liquid. Okay. So just another couple of slides here on this. Really, from the viewpoint of the local moments, at high temperatures, this individual localized moment has a spin, so you might expect Curie-Weiss-like behavior. And as you go down in temperature across sort of this characteristic Kondo scale, this Kondo scattering screens this moment. You get this singlet behavior. And so the susceptibility as a function of temperature is Curie-Weiss-like at high temperatures and rolls over to a Pauli susceptibility at low temperatures, this Fermi liquid behavior. And so indeed, if you were to look at the specific heat as a function of temperature, you have the full 2 degrees of freedom for the spin 1/2 impurities at high temperatures, and the entropy, you start to sort of lose that entropy at this characteristic scale of the Kondo temperature, and you recover a large specific heat value, C over T, in the low temperature limit of R log 2 divided by this Kondo scale, and this is then per spin, so then times the number of magnetic impurities that you have. From the view of the conduction electrons, you have this conduction band then scattering off of this local spin, and in fact this slows down the electrons so that you get what is known as the Abrikosov-Soule resonance here, and you see this enhancement of the density of states. This is a local enhancement of the density of states while we're looking at the single line picture. And so this already starts to give you the feeling of where this notion of heavy fermions are going to come from in the lattice picture. You see this large enhancement of density of states at zero energy. And actually, I very much like these review articles that are written by Piers Coleman that sort of walk you through this sort of formation of the heavy fermion state, starting in this sort of single line picture, which is well understood. So then when we move to the lattice, the picture is not quite as well understood. So here now we're looking at lanthanum, cobalt, indium 5, doped with some amount of cerium. And so this is resistivity as a function of temperature. And in the single impurity limit, sorry, the notation here is a little awkward. So 0.99 is now 99% lanthanum, so just a small amount of cerium. And here's the magnetic resistivity. You have this characteristic logarithmic increase of the resistivity, which is then saturating at low temperatures. This is just the magnetic part. So, in fact, certainly you have a phonon contribution, but then you subtract this by just measuring the non-magnetic analog. So, lanthanum hexaboride, you subtract this off, and you're just left with this logarithmic increase here. As you increase the cerium concentration, you still have roughly this logarithmic increase, but you can see it sort of peels away from the single ion behavior at higher and higher temperatures until you get to this dense Kondo lattice of pure cerium, cobalt, indium 5, so no lanthanum anymore. And what you see is that clearly now it looks like we're going to a new fixed point. We actually have a very conductive system, as opposed to a system where there was lots of scattering. We have a highly conductive metal in this case. And so I'd like, it's perhaps now proper to describe this as a new fixed point of the system, the dense Kondo lattice, as opposed to what we had in the single impurity case. And the sort of naive way of looking at this is in a simple beam field-like model, where what we originally have are we have conduction electrons coming from the background of lanthanum, cobalt, indium 5, and then we have this virtual state of f-electrons that was sort of like our Abrikosov-Soule resonance. And now we're going into a translationally invariant picture where we have a lattice of cerium ions. And so we hybridize these two bands. And so what you see is that then you end up with a very flat band that is crossing through the chemical potential. And so a flat band has a small Fermi velocity, and then the effective mass is 1 over that. So this is sort of just kind of a very kind of, I think, simple, intuitive picture for where heavy fermions are coming from. So in fact, this was then seen in the variety of cerium and terbium as well as uranium compounds. So here you see cerium aluminum 2, the specific heat as a function of temperature. There's the slope of this gives you a nice large T-linear term. You get a specific heat coefficient of 1.6 joules per mole Kelvin squared. So just as a point of reference, right, so the linear term in the specific heat gives you the electronic contribution, which is proportional to the effective mass. And as a point of comparison, copper, for instance, has a specific heat of 0.7 millijoules per mole Kelvin squared. So this is a factor of 2,000 times larger than what you find in something like a conventional metal. As a result, the Fermi liquid behavior, and we've heard people describe this as the resistivity as a function of temperature, or in this case, temperature squared. The electron-electron scattering just goes as t squared because of phase space arguments, and those phase space arguments then depend on how many states are available to scatter and to scatter into, and so you get the effective mass squared in the resistivity for the t squared component. And because this is so large, you can actually see this very clearly in heavy fermions. So if you look in copper, actually, you don't find the t squared coefficient of the resistivity because it's so small. But in the heavy fermions, you see very clearly this t squared behavior of the resistivity. Okay. So one other important ingredient for understanding heavy fermions in general is the magnetic interactions that can occur. So we described the behavior of forming just a Kondo singlet of one impurity, but when you have two impurities, you can have two possible outcomes. So either each impurity individually will undergo the Kondo effect and screen that local moment. And you have a characteristic Kondo temperature that scales as the exchange interaction between the local moment and the conduction electrons. Or what you can have is the so-called RKKY interaction. And so what you see in this plot actually is this local moment actually sets up Friedel oscillations in the spin polarization of the conduction electrons. And so you can see that now there's a mechanism to transfer the information of this local moment spin to a neighboring spin. Okay? And so in fact, you can, instead of forming singlets between the local moment and the conduction electron, then form singlets between the two local moments. And that scales as k squared. So 1 for the exchange interaction of this local moment to the conduction electron, and then again, the conduction electron to the neighboring local moment. So you get a factor of j squared. And in the lattice case, instead of forming just a singlet, you'd form long-range magnetic order. Okay, so then this brings us to the so-called Doniach phase diagram, where as a function of temperature and the tuning parameter, which is the exchange interaction, now J, you can see at low values of J, you will always be dominated by this RKKY interaction. And so in fact, you will generate magnetic order at low values of J. But eventually, the exponential term of the single line Kondo interaction should always win. So in fact, at some point, this magnetism will have to be forced to turn over. You'll suppress the magnetism as you form Kondo singlets. And what is typically found is actually this phase transition then tends to be second order. And you end up with a quantum critical point as the exchange interaction is increased. And at a practical level, for cerium compounds, you increase this exchange interaction simply by applying pressure to the material. The pressure increases the wave function overlap of the f orbitals to the neighboring ligands, and so the larger the hybridization of those orbitals, the larger the exchange interaction will be. Okay. So I was saying that already the conventional wisdom was that magnetism was bad for superconductivity. The Kondo effect was worse. In this lattice of cerium compounds, we're going to have the RKKY interaction. So we expect to have magnetic order, perhaps magnetic fluctuations. And so it came as a real surprise then that superconductivity would be found in such a system. So in 1979, Frank Staglish established actually that the superconductivity here, you see resistivity as a function of temperature. You see a nice superconducting transition around half a Kelvin. That this was actually superconductivity. In fact, superconductivity had been seen in other compounds, most notably uranium beryllium-13, was believed to be just an impurity phase. Because in fact, magnetism was so strongly believed to be pair-breaking and bad for superconductivity that in general, if you saw something, you figured you must have had some impurity phase in your sample and was generally disregarded. But the evidence that this was actually happening in the heavy fermion fluid is the fact that the specific heat jump here is quite large. So now this is C again versus T, so the linear coefficient here gives you gamma, again a gamma of 1 joule, so effective masses of about 1,000 of the bara electron mass. You see, for comparison, the lanthanum analog is actually this line that basically just hugs the x-axis here completely. And then the large jump tells you actually that it's the heavy quasi-particles that are participating in the superconductivity of this material. Okay. Even early on in this original paper by Frank, what he noticed was in fact that Tc relative to the Fermi energy in this material is actually quite large. So in fact, we've seen these plots now, the Urumura plot that several people have made. We saw in the magic angle of graphene that Tc relative to the Fermi energy is large. In fact, this was noted immediately. So in fact, even in this paper, he says that cerium copper 2 silicon 2 is a high temperature superconductor. So they already realized that this was sort of a route towards high temperature superconductivity, if you will, and then in fact is one of the main motivations for studying heavy fermions. Practically, you will not get to room temperature because the Fermi energy is so low. But if we were to understand unconventional superconductivity in the broader context, we really need to be able to understand the heavy fermions in the same framework that we understand peptides, cuprates, and perhaps graphene as well, or magic angle graphene. The other thing also that he realized is that this cannot be described by a conventional theory of electron-phonon mechanism, and primarily this was because now actually with the small Fermi energy, the Debye temperature was not small relative to the Fermi temperature. However, we will soon realize actually that this is more a statement than just the Fermi energy relative to the Debye frequency. And this came then a few years later when the discovery of superconductivity happened in a few uranium compounds. So here is work on uranium platinum-3, as well as uranium beryllium-13 doped with thorium. And what is very striking about these phase diagrams here, now this is magnetic field as a function of temperature, this is temperature as a function of doping with thorium. You see multiple superconducting phases. So in UP3, famously, it has 3 superconducting phases. They seem to actually all converge at a single point here in the phase diagram. And it's very difficult, if you have an S-wave superconductor, to see how you could actually imagine coming up with 3 distinct superconducting phases. So this was already one of the sort of first evidences that in fact actually the order parameter must be unconventional in these materials. And in fact, this was this early work here was predating the work on high TCs. These phase diagrams not in particular, but the specific heat data on uranium beryllium-13 actually, the low temperature specific heat of a conventional superconductor should be exponential. Here you see this BCS behavior. But in fact, turns over and becomes power law-like behavior in the case of uranium beryllium-13. That power law is indicative of nodes in the superconducting order parameter. And here, ABM is the work by Anderson, Brinkman, and Morel, actually suggesting that this is more consistent with a P-wave superconductor. And this followed on the theoretical work that was done on helium-3, where they knew that in fact that you had an unconventional order parameter for helium-3. They extended this now to superconductors in the case of the heavy fermions. Okay, and this is generically found in many of the heavy fermion superconductors nowadays. You find power laws and transport and thermodynamic properties that are suggestive of nodes in the superconducting order parameter. Okay. So then in the 90s, people started to realize that in fact the superconductivity in these heavy fermions, particularly the cerium-based heavy fermions, seem to be tied closely to magnetism. And so these phase diagrams, now temperature is a function of pressure. Because of the small energy scales, you can easily tune the ground state of the system with pressure, so you don't need doping. And what you see is that the antiferromagnetism is suppressed, and you recover a dome of superconductivity, cerium copper 2 germanium 2, cerium rhodium 2 silicon 2. And most famously, in the work by the Cambridge group here, you see cerium palladium 2 silicon 2. They also did this for cerium indium 3. And this is the work of Malta Grosha and Bill Lonsrich and others. Temperature is a function of pressure. You see beautifully coming down this sort of really beautiful dome of superconductivity. And we've discussed this now in the context of pnictides and recuperates. And many people have remarked that this is sort of perhaps our one place actually where we know how to find unconventional superconductors. This is particularly true in cerium-based systems. So if you get a clean cerium antiferromagnet, drive the magnetic transition to T = 0. It's a second order phase transition generically. You get quantum critical behavior. So you see here the resistivity is a function of T. In this case, this is T to the 1.2. You get this linear behavior. So you get some sort of power law. The power law is actually not universal. We don't always see T linear. So some systems see T linear. Others see T to the 3/2. That's consistent with sort of a more conventional Hertz-Millis-Maria like theory of quantum criticality. Sometimes we see sublinear behavior. So in the 115s, we see T to the 0.8. So the value of the power law is not well understood. So, but in fact, heavy fermions offer clean systems in which to explore quantum criticality, and we see that those fluctuations in some way promote superconductivity. Okay. So many varieties of heavy fermion superconductors exist, and so I think from the outside it can really look like a view of materials. I think this maybe provides some people with like sort of a bit of caution from jumping into the field. Each one has its own phenomenology. Each one is a little different in its own way. And so it's not obvious that the superconductivity actually has the same kind of pairing mechanism in all these. That there might be distinct features, but it shows the robustness of superconductivity within heavy fermions. So in the following talk, we'll hear about the ferromagnetic superconductors, systems like uranium-2, where here, in this case, superconductivity lives within the ferromagnetism. But there are also cases like uranium-ruthenium-2, silicon-2, where we don't even know the nature of the ground state. So there's this hidden order state, which is highly debated as to what the order parameter of this broken symmetry state is. But the superconductivity seems to live only inside this hidden order state. As it becomes a nice anti-ferromagnet, in fact, the superconductivity is suppressed. Here's a praseodymium compound, which has quadrupolar ordering in an applied magnetic field. You find superconductivity here. UPD3, I already mentioned the three different phases that you find in UPD3, where actually quite different order parameters are expected in those three different phases. Here's an example of cerium, cobalt, and Nium-5. In the high field, low temperature part of the phase diagram, there's magnetism that seems to live only within the superconducting state. So as you go above Hc2, actually, you don't find magnetism anymore. There's been evidence for pair density waves. So we heard about, arguments for pair density waves and cuprates. And I hope one message that you take away from this talk is that, in fact, a lot of the phenomenology of heavy fermions mimics itself in the other systems, in 3D systems. So whether it be pnictides or cuprates, there are differences, but in fact, you see the same kinds of phenomena sort of appearing in these systems. And so this maybe gives us a new way of trying to attack the problem, new ways of studying these systems.
What is the evidence for pair density wave?
So
you mean in the Q phase?
in the Q phase.
Oh, in the Q phase, yeah.
Only in the Q phase, yeah, that's right. So and
That's
then
because it is a magnetically modulated state of some sort.
it's a magnetically modulated state, and then the thermal conductivity measurements show that in fact where you anticipate the nodes to have the most nodal quasi-particles actually appear to be gapped out. And so you need an additional order parameter in order to gap out the quasi-particles. We know cerium cobalt Nium-5 is a D-wave superconductor.
Yeah.
And so in order to gap out those quasi-particles, based on the magnetic propagation vector, the one explanation is to have a pair density wave to actually gap out the quasi-particles that you don't see carrying heat. Okay, and there are a variety of others. Terbium aluminum boron 4 has a very low TC, and so this brings up the notion that terbium is the whole analog to cerium. So cerium has one f-electron, the terbium has one hole. It's an F13 configuration. People have often talked in the cuprates. Why can you not find a D1 analog of the cuprates that is also a high temperature superconductor? You have the same kind of thing in heavy fermions. There's a Neptunian superconductor with a very strong Ising like magnetic susceptibility in the normal state. Cerium platinum 3 silicon is non-centrosymmetric, so mixing of spin singlet and spin triplet components, because you break inversion symmetry, is present in the cerium compound. Uranium plating to aluminum 3 orders antiferromagnetically before you get superconductivity. So there's a variety of different compounds again, and so you can get lost in all the details. But I think just in general, it provides a rich environment for studying the different things that can occur. Okay. So, open questions. So naturally the outstanding question is, what is the pairing mechanism? And as I mentioned, it's not clear, in fact, that the pairing mechanism would be universal across all these systems. So I think what I'll show now, coming up, are again the same themes coming up that we've heard in previous talks throughout the week. And in particular, the one system that really, at Los Alamos, we've been working on a lot, are these so-called 115s. And these are really sort of a striking set of compounds to try and understand unconventional superconductivity. So cerium-indium-3 is a cubic system. It's an antiferromagnet. It orders magnetically at around 10 Kelvin. And here you see temperature as a function of pressure. So the work by the Cambridge group initially showed that the antiferromagnetism comes down and you have this beautiful dome of superconductivity. Maximum TC of this dome is 0.2 Kelvin. What was found out by our group in Los Alamos, and this predates before I even got there, was that they showed that in fact you could insert just a layer of rhodium. So just a layer of rhodium atoms between the cerium-indium-3, and that forms this so-called 115 structure. So for instance, cerium, rhodium, indium-5. And because this system is now sort of quasi-two-dimensional, it's a layered version of cerium-indium-3, the magnetism comes down, as you would expect, reducing the dimensionality of the magnetism. And when you apply pressure now, the magnetism is again suppressed with pressure. You get a dome of superconductivity, but the maximum TC is now 2 Kelvin. So we've increased TC by an order of magnitude just by inserting this layer of rhodium. So this is really an amazing example of how quasi-two-dimensionality is sort of boosting superconductivity. We know from the Coupe race, right, we have this prevailing view that layered superconductivity is good for, layered materials are good for superconductivity. Here you really see this beautifully exemplified in this system. Now, what precisely is the role of the dimensionality? Is it in the spin fluctuations? Is it in the electronic structure? That's actually not very well understood. So the Fermi surface of this material has nice cylindrical parts, so it does look 2D, but it also has very 3D pockets. So in fact, the transport anisotropy is only a factor of 2. The magnetic susceptibility, so whether you have Heisenberg-like spins or Ising-like spins, is also only a factor of 2. So it is still an open question as to how this reduced dimensionality really boosts superconductivity, specifically in this compound. The other thing which is nice about this material is that cerium cobalt indium 5, so if you replace the rhodium with cobalt, cobalt is a smaller atom but isoelectronic, so effectively acts like chemical pressure on the system. And so cerium cobalt indium 5 is at ambient pressure, 2 Kelvin superconductor, whose normal state actually shows non-Fermi liquid behavior and evidence that it's very close to the antiferromagnetic quantum critical point that you expect in the rhodium compound. So a lot of work for the superconductivity is really focused on this material, cerium cobalt indium 5. Yes?
I seem to remember that people actually make some super lattices, right?
Yes.
Artificial super lattices.
That's right. Yeah. So
was it this compound? I think it was
yes.
very similar. Right?
Yeah, no, indeed. So it was Yuji Matsuda, and so unfortunately he's left, but he was able to make super lattices of, say, cerium rhodium indium 5 and cerium cobalt indium 5. And they see very interesting effects because now actually you break the inversion symmetry, and so there were arguments that actually this leads to a Rashba coupling, and he sees interesting behavior in HC2 in these thin films that he was looking at. So in general, unfortunately, MBE is actually very difficult for these compounds, and he's to date the only group that has been able to make really beautiful thin films of this. But he's also looked at sort of how the superconductivity in cerium cobalt indium 5 evolves as you basically reduce the dimensionality. So as you go to a single layer of cerium cobalt indium 5 buffered by non-magnetic layers, you can see how TC is suppressed and all these sort of things. So that's a very interesting direction. I don't have it here, but thank you for bringing it up. Okay. The story, at least when you're at Los Alamos, doesn't end with cerium rhodium indium 5. In fact, you can make a plutonium analog of this system. Plutonium cobalt gallium 5 forms in exactly the same crystal structure and is in fact a nearly 20 Kelvin superconductor. So in fact, you went from now 0.2 Kelvin to 2 Kelvin to 20 Kelvin, all within the same family. And the very sort of naive view here is that plutonium, being a 5F analog of cerium, has more extended wave functions, so larger degrees of hybridization, the spin fluctuation energy scale is larger, and that's boosting TC another order of magnitude. So we have 2 order of magnitude increase in TC, And certainly if we are now driving towards high temperature superconductivity, you can see that this is actually a very rich family for investigating superconductivity. And in fact, there are bilayer variants and trilayer variants and these sorts of things. So there is actually even more to look at.
So there's no transition metal version of that structure?
No. Yeah, that would be great. So, okay, so this is then a plot to sort of really show that in fact the superconducting transition temperature seems to be set by some spin fluctuation energy scale, a spin fluctuation energy scale that you extract actually from the electronic degrees of freedom. In this plot, okay, it's a log-log plot, and we should always be cautious about over-interpreting, especially when there is a fair amount of scatter in these plots. But roughly speaking, you can extract a spin fluctuation energy scale from the NMR, from the specific heat, even from, in this case in the cuprates, it was extracted from the T-linear term of the resistivity, but you could extract it in other ways. You see all these compounds really sort of fall, roughly on the line that says, the characteristic energy scale of the spin fluctuations coupling to the conventional electrons is setting the scale for TC in all of these compounds. And the ferromagnetic superconductors sort of sit a little bit below this kind of characteristic relationship. Okay, so one of the additional open questions is really the role of spin fluctuations versus actually charge fluctuations. And this will maybe at first seem rather strange that now why am I mentioning charge fluctuations? Because I really only had sort of in cerium a moment of a system of local moments, right? So here again it's temperature as a function of pressure. This is again cerium rhodium 5, magnetism, superconductivity. If we remember this picture, this sort of mean field picture that we have, if I had not hybridized my f-electrons really at all with my conduction electrons, I would have had a Fermi wave vector that would have been sitting here. Okay, sort of what we now sort of in the heavy fermion community will call a small Fermi surface. But once we hybridize this system, in fact, we actually generate sort of a new Fermi wave vector. The size of the Fermi surface actually increased, and it increased actually by 1 electron. Okay, so the spin fluctuations of the local moment actually get absorbed such that the size of the Fermi seat increases by one electron. Okay, and so in fact you would imagine that at some level with very small exchange interactions, you'd sort of expect to have a small Fermi surface. And at some point when the exchange interaction was large enough, you'd expect to have a large Fermi surface. And I've drawn it here that perhaps actually the crossover from small to large could happen right where the magnetism is suppressed. Now, there's no reason really why it should have to happen exactly at the same place, but it would be one possibility. And in fact, for the case of cerium rhodium 5 as a function of pressure, it seems to be exactly that way. So here are quantum oscillation measurements. This is the DHVA frequency, which is measuring the Fermi surface morphology. And as a function of pressure, it changes discontinuously at 2.3 GPa, which is precisely the point where the magnetism is suppressed to 0. And we have specific heat measurements as a function of field and pressure that really show that 2.3 GPa is the place where the magnetism is suppressed. Okay? So this actually shows that not only do we have spin fluctuations, but we have a reconstruction of the Fermi surface precisely at the point where you go from small to large. And this is not just the magnetic zone folding that you would expect from antiferromagnetism. You actually get this incorporation of the f-electron degrees of freedom into the Fermi surface. So we have both spin fluctuations and presumably some form of charge fluctuations at this quantum critical point, which is also perhaps making the understanding of the normal state even more complicated, but something that may also play a role for the superconductivity. In fact, it's an interesting question of whether the spin fluctuations or the charge fluctuations are perhaps promoting superconductivity more. And that was really brought out in some work on cerium copper 2 silicon 2. So cerium copper 2 silicon 2 also has the antiferromagnetism and the dome of superconductivity. But in fact, it always had sort of a strange dome, and it's not shown here, but the original dome was sort of a little bit asymmetric and actually sort of looks like it extends to very large pressures. What the group in Dresden were able to do was they doped the system with germanium, okay, and that acted as some form of pair breaking in the system, and it suppressed TC. But they didn't add so much that they killed off TC altogether. What they found actually was they ended up with two distinct domes. They ended up with one dome which was centered right around this antiferromagnetic quantum critical point, and the second dome at much higher pressures, which actually seems to be associated with some sort of valence instability. So they believe, although it's not completely confirmed, that you have charge fluctuation sitting out here, and it's certainly clear that the TC around this charge fluctuating instability is much larger than the TC around the magnetic instability. The magnetic instability is one of a more conventional nature. So this large to small Fermi surface, even though it's not been measured here, the other properties of this magnetic quantum critical point seem consistent more with sort of what you expect for an itinerant antiferromagnetic STW-like quantum critical point. So perhaps actually it is the role of the charge fluctuations that are more critical. Okay. Competing phases, I bring this up mainly because we heard earlier in the week about nematicity in the nuclides in particular, and the role that nematicity might be playing in superconductivity. In heavy fermions, again, we have an example of something that looks a lot like a nematic phase transition. So here's resistivity as a function of magnetic field. This is this antiferromagnetic compound, so we're sitting in the antiferromagnetic state. And you see a dramatic change in the resistivity. Now this is rho A and rho B in a tetragonal compound, so nominally they should be identical. The magnetic field is tilted a little bit away from the C-axis, so in fact actually, so you expect one leg to here to have a little bit more transverse magnetoresistance than the other leg, so small splitting. But at 30 Tesla there is a clear first order phase transition where you have a jump in the resistivity. It changes by essentially a factor of 2 in the two legs. And this was really enabled by some beautiful work from Philip Mall, where he used this focus ion beam milling. There's a crystal of cerium, rhodium, indium 5 that you can kind of see outlined here. He fibs out this small piece, it's about just 2 microns thick, lays it down on the substrate, and then fibs it again, so that you can actually do high field measurements. Now, this is really important because to do resistivity measurements in high fields of a highly conducting sample is incredibly difficult. So you have large signal to noise, small signal to noise in general. So you actually want to increase the overall resistance in the sample, and that was the motivation for making this fib structure, as well as the fact that you have large eddy current heating if you're doing this in pulsed magnetic fields. And so we wanted to go to large fields. In Los Alamos, we can go to 65, maybe even 100 Tesla. And so the eddy current heating is a huge problem when you want to sit at temperatures of order 1 Kelvin or less. But here actually, so you could pass the currents along this loop. Here, measure the voltage here, measure the voltage here. They should be identical. They are identical in zero field. But you see this huge dramatic transition. And the first thing you would say is, oh, well, you must have some sort of magnetic structural change there that is causing this. It's 30 Tesla, so it's very hard to do neutrons. But NMR has been done. There seems to be no change in the magnetic structure as you cross here. Magnetic susceptibility, torque magnetometry has been done. There's really no change in the magnetic structure from the magnetic susceptibility. Magnetostriction has been done. There's a small anomaly in the magnetostriction, but it's so small that it doesn't seem like that is what could be driving the transition. And so all sort of signs point to this is something happening in the electronic degrees of freedom. In fact, the only other signature that we have are the quantum oscillations change as you go through this 30 Tesla transition. So some form of order, and so now when you look at the temperature, pressure, magnetic field phase diagram, here we have magnetism and a dome of superconductivity, And now here we have some form of pneumatic-like response in this system. And recent work, continued by Filip, is to actually try and do these measurements now as a function of pressure. And now, so you're taking this FIB microstructure, putting it in a pressure cell, doing this in pulse magnetic field. So experimentally, this is an incredibly challenging experiment. And here's a phase diagram that we found. So in fact, in some ways the hope was that somehow perhaps this nematicity would be tied to the superconductivity. But in fact, if anything, we see the onset of this pneumatic-like response increase as we're increasing pressure. So it goes to higher fields, maybe sort of almost being repelled from the superconductivity, it looks like here. And in fact, the magnitude of this response shrinks with increasing pressure and essentially vanishes here. It's actually very close to the pressure at which the superconductivity has a maximum. And so perhaps actually this change of the electronic structure from small to large is actually also quenching this pneumatic-like response. It's possible that they're tied, but it's also difficult to make that direct comparison because we're now in fields of 30, 40 Tesla. It's not obvious that the pressure scale that is changing the exchange interactions in zero field should be sort of equivalent, and then you should necessarily just draw straight lines here. In fact, at even higher fields, we see evidence for a re-entrant magnetic state when you're sitting at large pressures and large magnetic fields. This still needs to be investigated, but there's an anomaly in the resistivity that looks like the antiferromagnetism maybe lives to even higher pressures than originally thought. Yes?
And how do you understand the negative magnetic resistance about the transition? So because it seems that you go over the resistance that you are observing. So how do you understand it?
We don't. This is actually incredibly remarkable. So this is the suppression of the antiferromagnetic order happens here, and you're absolutely right. In fact, this resistivity sort of reaches some sort of minimum here, just above 50 Tesla. You would anticipate, especially we see this also even when we have completely transverse magnetoresistance. So with the transverse magnetoresistance, you would expect a huge orbital sort of effect, and the fact that the resistivity matches this incredibly clean resistivity value here is not understood. And in fact, it dips down here and then shoots back up as you go towards 80 Tesla and reaches a resistivity value comparable to the resistivity and room temperature. So there's something very anomalous here that quite frankly I can't give a good explanation for. It's very interesting.
To apply the pressure, you just put the thing in the pressure mediating medium and it doesn't have pressure or something?
Then you just do that, that's right. So, no, so these were actually done in sort of diamond anvil cells. Indeed, actually, so you could fit the culettes of the diamond so to pass your leads through. True, cracking the FIB samples is an issue. Surprisingly, these small samples, and it's not clear why, actually seem to be a little bit more robust to strain. And I'll show an example in just a slide that you might be able to sort of twist these structures a little bit more. So in fact, maybe they are a little bit more robust to pressure inhomogeneities and other features. Now, I think my understanding of the real trick is that once you sort of cut this thing out with a FIB and try and transfer it to the substrate, is how do you actually pick it up, a sample that is sort of 20 by 20 by 2 microns. Sometimes it's sort of electrostatic force, ping, and it goes flying and you never see it again. So it's challenging from sort of how to manipulate it, but then they seem quite robust once you actually have the structure. Yeah.
Can you issue superconductivity?
Yes. Yeah. So
you have the situation where the resistance falls to zero.
the resistance falls to zero. Yes, down in this. In this structure under pressure, and we've also done similar ones on the cobalt, and you see very clearly the superconductivity there. In fact, we're hoping to do critical current measurements on the FIB structures. Haven't found anything interesting. Okay, so so one thing which actually maybe is interesting, perhaps from an applied perspective, actually, are these highly tunable ground states. So now I'm looking at another version of the system, serum iridium indium 5. And this is now, again, sort of one of these fibbed lamellas, so a small rectangular structure. Sorry, there's no scale bar here, but again, this is sort of 20 microns or so. And what was found actually was, this is some scanning squid work that was done by Katja Novak, where she saw the superconducting response. Now, this is a system which is superconducting in the bulk at 0.4 Kelvin. She saw superconductivity that was anisotropic across this lamella. And what they realized was actually this small lamella, when it's placed on a substrate, undergoes differential thermal contraction between the substrate and this structure. And in fact sets up a strain profile, and this strain profile, which is modeled here with some finite element modeling, knowing the fact that actually TC is very sensitive to strain, so we know from the thermal expansion exactly how sensitive to strain the superconductivity should be, that in fact the sample is in fact more strained here on the edges than in the bulk of the material, and in fact so you see the superconductivity show up sort of non-uniformly in the material. And in fact they go on to make one of these devices here now where you have a C-axis resistivity leg and an A-axis resistivity leg. So cut from the same material, in fact, you can vary TC by a factor of 3 in the system. So the hope is actually that we can put now devices like this, perhaps on a piezoelectric, thank you, and then be able to drive the superconductivity and modulate the superconductivity in such a system. And in fact, so Filip Mall is in fact even making, this is now a picture of cadmium arsenide, but you can envision a similar type of structure now where the purple is a serum iridium indium 5, you apply a gate voltage sort of below the system, and you could now actually bend your sample up and down, and the thing which we are going to try and do is actually now be able to tune the superconductivity on and off just with this gate voltage. So in general, you sort of imagine, okay, heavy fermion superconductors, this is not the place for applications, but in fact the tunability of the ground states means that for quantum technologies, this might be an interesting route, and this is something that we're in fact pursuing. Okay, open questions. I'd be remiss not to mention the fact that the superconducting order parameter, I showed a huge variety of different compounds. In fact, there are only really 2 where it's sort of relatively well established what the superconducting order parameter is, and that's serum polonium 5 is pretty compellingly a dx squared minus y squared order parameter. There are even a few phase-sensitive experiments. And UPT3, which is believed to be a spin triplet superconductor, has this sort of E2U representation for the order parameter to be able to explain the 3 different superconducting phases. But if I could make a plea, in general, there are very few phase-sensitive experiments on heavy fermion superconductors. And we would love to see the kind of experiments, so the Van Harlingen type of experiments, that really could establish that the order parameters change sign in these systems. And I think it's a materials issue in general. We're working with cerium, working with uranium, getting the interfaces of these materials so that you can generate phase-sensitive experiments is difficult. But perhaps in things like with STM, where you can look for Andreev reflection and you can look for signatures of the change in sign of the order parameter, is a way actually to explore these materials more generally. And it really is an issue because we take the example of cerium copper 2 silicon 2, and we heard earlier that now it is now believed not to be sort of a D-wave superconductor. So cerium copper 2 silicon 2 is tetragonal. It sort of looks a little bit like cuprates, and for a long time was thought, okay, it must be a D-wave superconductor, but then these low temperature specific heat measurements done in Japan really showed that actually at the lowest temperatures you're really rolling over into sort of what looks like a fully gapped scenario. So this can't be just a simple dx squared minus y squared. It's still believed to be unconventional, but how to reconcile these measurements now with the order parameter, with neutron scattering, which sees thin resonance, is an open question. And so there are a lot of interesting experiments left to be done here at Heavy Fermions. Okay, the last thing I'd like to mention is we heard yesterday about topological superconductivity. These are f-electron systems, so we have strong spin orbit coupling and then superconductivity. So these are really the ingredients that you need in order to, in general, find topological superconductivity of a variety of forms, whether this is specifically for Majorana fermions or other things. And I'm not sure how much Alexander will talk about this in the next talk, but there's some interesting results on a very new superconductor. This was just discovered last year, uranium-tellurium-2. And there's some STM work by Vidya Madhavan where now they're looking at step edges on the system, and they claim evidence for chiral edge states on these step edges. So I'm sure this is still controversial, and I certainly can't defend it, but I think it's a very interesting direction to go in these materials. And there are other systems, UPT3, uranium, ruthenium-2, silicon-2, for which there are concrete proposals on the topological superconductivity. We now need to find the right tools that will be able to find the signatures of the topological superconductivity. Okay, so I just end with to summarize maybe, you know, I'm trying to advocate for studying heavy fermion superconductors, and I think one of the strongest advantages is in fact the small energy scales. It makes the systems highly tunable with clean tuning parameters. So you can use pressure and change the ground state of the system and actually explore the system. Now, the small energy scales obviously are difficult for some experiments, and doing measurements under pressure is just not feasible at all. I mean, you can't do an ARPES measurement under pressure. And in fact also, so this turns out to be as well a disadvantage for the system, right? So the small energy scales does mean that it is difficult in particular to characterize the normal state. So, you know, the formation of the heavy fermion state as a lattice phenomena is not well understood. And it's not even well characterized. So we don't have the ARPES data that can sort of map out exactly what the electronic structure is, look what the self-energy is. So that's certainly a struggle. And in fact, the electronic structures tend to be complex. So we don't have the single band version of a heavy fermion, sort of where you just have a large hole-like Fermi surface centered at pi as you do in the cuprates. In general, we have multi-band Fermi surfaces that are quite complex. We know that from the quantum oscillation studies. However, we have stoichiometric systems. That means we have really high purity that in fact, you know, mean free paths greater than a micron. That's good for quantum oscillations. It also allows you to see states that you wouldn't otherwise see. So this Q phase, this pair density wave that we were mentioning in serum cobalt 5, in fact, it disappears with less than a fraction of a percent of impurities in the system. So we put in non-magnetic dopants, tin on the indium site, it completely kills the state. So in fact, being able to see new states sometimes requires this incredible cleanliness. I already emphasized this, the family of 115 materials, TC varying by 2 orders of magnitude. One of the big take-home messages, the physics is often analogous to the physics that we see in 3D systems. You know, TC over the Fermi energy in serum cobalt 5, again 0.05 is comparable with that you see in cuprates. And finally, I think an interesting direction will be to look for topological superconductivity in these systems. Sometimes you deal with uranium and plutonium. That's, you know, not everyone can work with plutonium, I understand. Uranium is actually relatively safe to work with. We ship samples around all the time. They can be radioactive, but certainly you're not going to swallow, I think, any of the crystals that you're working on. But this radioactivity can even be a feature. So in fact, you can do an impurity scattering study on the system just as a function of time. TC in the plutonium superconductor is suppressed by 1 Kelvin every year, that you just leave the crystal sitting on your bench. And so you can actually look at how the scattering is compared to, say, Avogadro-Volkoff theory and demonstrate that you have some sort of unconventional like behavior. So sometimes it can be a feature. So with that, thank you for your attention.
Hey, thanks for a very nice introduction to the fermion materials and superconductors. Student questions first.
And the plutonium cobalt gallium 5 is under pressure or atmospheric pressure that you see?
Is atmospheric pressure. So you know, the strength of the tunability of the ground state is sort of removed somewhat as you go to 5F. So so the plutonium cobalt gallium 5, they've done pressure studies. TC goes from 19 Kelvin to 20 Kelvin after about 2 gigapascals of pressure. So you can tune it a little bit, but in general you don't see these beautiful quantum criticality things emerging. The plutonium superconductors actually are even richer. So the plutonium cobalt gallium 5 is 19 Kelvin. The rhodium one is about 8 Kelvin. You can actually make indium analogs where you expand the volume of the unit cell by 20%. So this is an incredibly large expansion. TC is then 2 Kelvin. And so at some point, you'd expect to see the magnetism as you're expanding and localizing the system, and you don't see that within the plutonium 115s. So it's in fact perhaps an argument that there's evidence that maybe there's valence fluctuations. So again, this idea that the charge fluctuations are driving the superconductivity there. So it's not obvious that it's exactly the same kind of magnetic quantum critical point scenario in that. So it is more complicated than that.
You showed your graph with all the different heavy fermion superconductors, and you said that there was UPT3, which had the 3 phases in the superconducting state, and that there's some evidence of knowing which kind of superconducting state is realized in which phase. Which measurements then give that evidence for these phases?
So I think so I'm not enough an expert on UPT3 to call out which specific one, but I mean basically I think it's the ensemble of experiments that are compelling. So particular measurements that are useful are NMR, and NMR has seen the sort of the lack of the night shift, which we heard now in strontium ruthenate is something that, okay, is that something we actually have to revisit or not? I don't know. But so NMR and the T1 ultrasound measurements, where you actually have some directional probe of the sort of where exactly the nodes of the order parameter are sitting in momentum space. So there are some directional probes like this, thermal conductivity at low temperatures. I think those are the kinds of measurements that sort of start to rule out sort of which of the order parameters are most likely. So the fact when I say E2U, that's the one that's most consistent, I think, with most of the experiments. I couldn't tell you that it's consistent with all of the experiments, but that's sort of the generally agreed upon. And there have been phase-sensitive experiments. Van Harlingen did look at UPT3 where he could then actually, he did a curved surface and he looked for sort of these, similar to what he did in the Coupe rates in terms of how matching it with a conventional superconductor, indium or lead, I forget which one, how the current sort of is evolving in these sort of squid like junctions that he's creating. So there is sort of a large body of experiments that sort of point to this E2U representation for the order parameter.
May I add something? I think it's still the only superconductor where you have 3 second-order phase transitions within the superconducting phase as measured by specific key.
Kerr effect.
Yes,
And the rejector.
We know that the time reversal symmetry is broken.
that's right, yeah. So you know, which is one of the big arguments that it should be a topological superconductor is because of the broken time reversal symmetry as well. I think, or at least one of the supporting arguments that leads to these.
It's time reversal symmetry broken.
Yes.
Okay.
More questions also from others, yeah.
On theory coupled to silicon 2 first.
Yes.
So there's seemed to be a fully gapped state.
Mm-hmm.
But what Yuji Matsuda was pointing out was the robustness against impurities.
Mm-hmm.
So that, to my taste, supports most clearly a good old-fashioned S-wave superconductor. And well, I mean, it's got a low DC, there are 4 loads. Maybe it's a complicated theory to explain that.
Mm-hmm.
But what is the evidence? I mean, the resonance mode is something we can discuss independently because we do not yet know what the superconducting gap is, I believe, with the precision, and we want something below 2 delta.
Yes.
A sharp peak in the imaginary part of susceptibility is not alone an indication for resonance mode. So what is your feeling on theorem coupled to silicon?
So I guess I'm trying not to take an opinion on this. You know, so I agree that there's sort of a subset of people that sort of are kind of starting to lean towards S-wave in the system. Although, I mean, Frank, perhaps not surprisingly, argues that in fact impurity studies that he's done, sort of, you know, for instance, the germanium doping, it is sensitive to some impurities. So in fact, the fact that it's robust to impurities is not a state to non-magnetic impurities. Is not a statement that it is robust to all non-magnetic impurities.
Okay, so the jury's still out on the impurity story.
Yes,
I see.
I think so. So I think basically it depends on which data set you look at, and you can basically convince yourself either way. And that itself is kind of interesting that it would be sensitive to those kind of particular details. I don't have a particular view of it's S-wave or D-wave. I agree, it could in fact be S-wave.
If I may, one more. The ordering vector of the low field cerium rhodium 5, do we know it?
Yes.
Where does it point? What's the
So
ordering vector?
the Q wave vector is half 0.297. So it's incommensurate out of the plane. It's pi ordering in plane. And the spins are...
So it's pi ordering.
In plane, it's pi ordering. And the spins lie in the plane, and then it's essentially a helix as you go along the C direction with a periodicity of about, you know...
So this makes its pneumaticity very mysterious then, right?
Yes. Yeah. No, I mean, I try to say it's a pneumatic-like response.
Yeah.
Whether it really is sort of electronic pneumatic, I don't know. And one of the other things I didn't mention was that we see the same response in sort of B1G and the B2G channels. So whether we make a device with row A and row B, we see this response, or we make another device at 45 degrees and look along 110 and 1 minus 10, we see the same kind of response as well. So
this is almost illegal behavior.
I agree. Yeah. So yes.
When you say the same response, are you tilting the field? Is that what you're doing?
Yeah. So in fact, if the field is aligned directly along the c-axis, we see no anomaly. So the size of this pneumatic-like response depends on the tilt angle as we go. So and make sort of one of the legs longitudinal versus one of them transverse. So we have to have.
Then it's legal.
So
it's like starting with 3 to 7.
yes. Yeah. We do need a symmetry breaking field in order to see this. Although the symmetry breaking field can even be the current itself. So in fact, if we put the field directly along the c-axis and drive it with a large enough current, we actually start to see, it looks like a kind of a density wave-like response. We actually see the resistivity drop just by driving large currents, and that happens above 30 Tesla as well. There are other ways to manipulate this, but there has to be something symmetry breaking in order for us to see it, which is true kind of all the pneumatic states as well.
Is there a last pressing question? Otherwise, I think no. Otherwise, I think we should move on. So let's thank Filip again.